Section 9.5. Number 10, 792. Number 18, 45. Number 18, 45. Number 24, let me give you a moment to check the expansion. You could have used NCR, or you could have used Pascal's triangle. It would have been 1, 5, 10, 10, 5, 1. But you would have also had to raise 2 to the powers and simplify. Ooh, you guys have a few things to grade. Let me give you a second. 24, 32, and 50. Is St. Patrick's Day tomorrow? Okay. It's tomorrow, not today.
I may eat her for that.
Ooh, you're going to be eating Cuban food on St. Patrick's Day. That just seems wrong. But you should still come. Have corned beef on Sunday.
Does it count if your eyes are green?
I've heard no. I wish yes.
My dad says yes.
I wish yes. Band-Aid. You guys should be pretty close to being done checking the expansion. You want to wash it?
I got my ACT
Here.
next month.
There's a wipe to wash. And then there's Band-Aid. You're up. Scroll down. Anybody still grading on these ones? All right, last two, 54 and 88. Last two are up, 54 and 88. Last two are up, 54 and 88. All right, let me see what questions you guys have. Some of you are still grading, that's okay. Did they turn out okay, the evens that you were wondering about?
Not homework. Is
Go
it
ahead.
possible to take a factorial of a decimal?
No. Factorials are only possible of whole numbers because of the definition. Good question, though. I'm not sure what your calculator would do. I'm curious. Why don't you try it? I'm not sure if the programming... Oh, good. Error? Good. Definition of a factorial is the product of all the integers. Nope, you wouldn't say integers. All the whole, yeah. I'd say all the natural numbers, right? Because it doesn't go back to 0. So it'd be the product of all the natural numbers from 1 to n. You can have a negative in front of a factorial, but you can't have a negative number in a factorial. Does that make sense? So if you typed it in your calculator, it should work, because if you do negative, then like 5 factorial, it's defined to be the factorial then the negative, so it would be like a negative on the outside. But if you did negative 5 factorial, I think it should be error also. Colby.
Is 0 a whole number because it's empty? I mean, like there's nothing there.
Yeah, but if you do a whole number, if you do all the whole numbers up to, you would multiply by 0, so then everything would be 0. Whole numbers include 0. I'll put it that way. Whole numbers include 0. Natural numbers only include 1. Yeah. When it's negative in parentheses? Ooh. That might be a programming glitch then. Because if it's a negative on the outside, you can do it negative on the inside. I'm not sure that's defined. Huh. Be an interesting thing to research. I'm not sure it's defined, though. I would say it's outside the definition, so it should be error, but it might be a programming glitch. Interesting. I think those are all the evens, and I already asked, but I'll ask one last time. Any evens or odds? Oh, there we go. Okay, Patricia, what do we got? 50? What else? Melanie? 59? What else? David?
I think it was 89.
Anything else? Okay, number 50 we have up here on the screen, so let's go check out what's going on in that one. Number 50, you were trying to get to the 5th term. Do you guys remember what my hint was when we were talking about the nth term in a progression? What I said to do with r? Fifth term, r would equal what? R would equal 4. Because remember, n needs to be this 5 all the time, all the time, all the time. So then you would go ahead and do NCR. I mean, this is why the formula is what it is. NCR, x to the n minus r, y to the r. And remember, in Pascal's triangle, if you get down to 1, 5, 10, 10, 5, 1, r is equal to 0, r is equal to 1, r is equal to 2, r is equal to 3. In this expansion, you have everything, all the powers, so 5, 4, 3, 2, 1, and also 0. So you have 6 different terms. The fifth term would be 1 away from the last. Ooh, I apologize. That's not supposed to be there. There we go. 6 terms, but you end at r equals 5. Yeah. Oh, that's what 6 to the 4th is. Whenever you raise a number, so the 5 to the 1 was easy. It's just 5 stayed and a stayed to the first power. But when you do 6b to the 4th, it's 6b, 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 6b. So 6 gets raised to the 4th, which is that number. Does that make sense? So then you have your 5 because it's in the 5 spot, or by solving NCR. And then you have that 5 from being the first power, and then you have this from 6 to the 4th power. Yeah. Okay, number 59, and then 80. What was it, David? 89? Okay. Oh, I'm sorry. I thought I had it opened already. Section 9.5, right, guys? Okay. Number 59. That's a little extreme. There we go. All right. Remember what we just said, just did. And whenever you're trying to get to a term, the easiest way is to think of who is r. So for any of these, NC, x to the n minus r, y to the r. That's the general formula. However, when I see all of these x's and y's and 3's and I'm like, z's and t's, I'm going to change this to be a and b. That way we don't think about it necessarily the same way, because whatever is in this first spot is going to be the a, and whatever is in the second spot is going to be the b. So I'm going to make it a to the n minus r, b to the r. That way we have no predetermined sense of what's supposed to go on. A is whoever's in the beginning, B is whoever's in the end. So for number 59, when we see x to the 8th, some of you might have focused here and gotten a little bit thrown off because x squared is your A, which means the highest power of x is not going to be 10. What's the highest power of x going to be? 20. Does that make sense? Because x squared is going to get raised to the 10th power. X to the 20th is going to be the highest. It's going to go x to the 20th, x to the 18th, 16th, 14th, don't know my even numbers. Anyway, all the way down to x to the 0. So what I would say is don't look at this, don't look at the n minus r. I would say look at that. Because if I go plugging this in, I'm going to have n, which is 10. R, I'm not quite sure. A is going to be x squared to the 10 minus r. And y, positive y, is going to be raised to the r. I'm going to look there because that matches up super nice because it's just y to the r. So y to the 6th, r must equal 6, right? But over here, if I was to look at the x, well, this doesn't equal 8. This combined equals 8. So you could have set 20 minus 2r equal to 8 or just r equal to 6. Both of them should be the exact same thing. Let me check it. Power to a power you multiply. So either this works or this works. It should happen the exact same way. Subtract 20, negative 2r equals negative 4. Ooh. No, no, no. Lo siento. Negative 16. I am struggling so hardcore. Thanks, guys. You said it right, and I still said the wrong answer. Negative 12. Hence, r is equal to 6. So however you see it, r is equal to 6. So to solve for this one, all you have to do is 10c6, x squared to the 10 minus 6, 4. X squared to the 4th is x to the 8th. y to the 6. Dun, 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 dun. Is that good? I forget who asked it. Is that good? Okay. And then our last one's number 89. So I think the takeaway from this entire section is to get your first term into the A spot, your second term into the B spot, compare, and say who was R. I think that's probably the best way to do it. Kind of? Is that okay? Okay, number 89. Let's go see what's going on. Ooh, hey, look. Describe the pattern formed by the sums of the numbers along the diagonal line segments shown in Pascal's triangle. This is just trying to introduce you to, there are a lot more just what you see. But anyway, what happened when you guys added to the side? 1, 1, 2, 3, 5, 8. 1, 1, 2, 3, 5, 8. I bet the next one's 13. I bet the next one is 21. I bet the next one is 34. I bet the next one is, what am I doing in my head? The Fibonacci sequence is in Pascal's triangle too. You're welcome. Yes, it is. Okay, that's all. Was that it? I think that was it.
Is it on purpose?
It's not on purpose. There are just a lot of patterns that are present. Fibonacci shows up in all sorts of weird places. Anyway. Dun, 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 dun. All right, cool kids. Here we go. Ooh. Ahem. What you see? What's up here? Probability. It's coming a lot sooner than you guys thought. And than I thought. Then I remembered. Probability. Sections 9-6 and 9-7. 9-6 tells us how to count stuff. 9-7 tells us how to figure out ratios, percentages of stuff. 9-7 is chances. 9-6 is how do we even think about counting? Yeah, this is 9-6. You can think intro to 9-6 if you want to write it down somewhere. You can just go in your workspace. If you're like, ew, gross, it's not very organized. Fine, go in your workspace. That's okay. You don't have to start off 9-6 yet if you don't want. 9-6, technically, I apologize. It's called counting principles. Counting principles. You can put it in your notes if you would like, or you can just go back to your workspace if you want and call it Intro to 9-6. Counting principles.
What if there's 8 full times, and then in the next one there's 4? It's just not going to be a different place.
All right, you guys got answers?
We're arguing. It's more the 8 different than 84. It's the same piece of paper. But it's the same two pieces of paper.
Are you guys on A or on B, though? That's the real question. Okay, so what's the scenario? What do you got? Scene. I have 1, 2, 3, 4, 5, 6, 7, 8 in a hat, a box, whatever. Pieces of paper, right? You draw one piece, record its number, put it back in, and then draw again, right? What are all the different possible pairings? Some of you started talking about it. What do we got? 1 and 8 sums to 9. That's not good. 8 and 4. 7 and 5. 6 and 6. Those are my possible pairings, right? In some order, getting 6 and 6, 7 and 5, and 8 and 4. Those are my possible pairings. Those are the only ways that I can make 12 from those pieces of papers. Now, those are the possible pairings. How many ways is it possible?
2.
How many ways is it possible?
5.
Okay. You pick out an 8. You pick out a 4. That's one way, right? You pick out an 8, then you pick out a 4. What's another way? You pick out a 4, then you pick out an 8. That's another way.
Isn't that the same way?
No, it's a different way. Because either you get an 8 first. Oh, man. You get a 4. Whew. Or you get a 4 first. Oh, man. You get an 8. Different ways. Okay. That's pairing. Okay. What else? 7 and 5. Or 5 and 7. 6 and 6 is 1. Getting a 6, and then getting a 6.
That's why it's different.
I thought you pulled out the 6.
You can replace it. That's only one. Nothing about this way, okay? Ready? If you were to put out all the different possible ways you can pick the papers, wouldn't you have 1 going with 2, 1 going with 3, 1 going with 4, 1 going with 5, 1 going with 6, 1 going with 7, 1 going with 8? Those are like all these ways, right? We're going to have the 2 going with 1, 2 going with 3, 2 going with 4. I mean, if you were to list all the different possible ways, this would be in there and that would be in there. Does that make sense? So how many ways? There are 2 different times, 2 different possibilities as far as how to get 12 from the pairings of 4 and 8. Does that make sense? 2 different ways to get it from the pairings of 5 and 7, but only one way with 6 and 6, because there's only one piece of paper with 6. So you put it in, you happen to pick it out again without like cheating and just like putting it on top, being like, yeah, there it is. Okay, so 5 different ways. Now hold on, wait. What if I was to ask you, what are the chances? What are the chances of getting 2 that sum to 12? You wouldn't say 5, that'd be 500%. That's totally not even realistic. Or what? Okay, what are the chances? What would you have to think about?
5 over total number of possibilities.
Yes, 5 over the total number of possibilities, but what would you have to do in order to get that chances? Pretend that's spelled right. Because chances, doesn't that need a percentage, right? 50% chance of rain, 75% chance of rain, 100% chance that tomorrow is Havana Nights. Well, maybe I shouldn't say 100%. Hopefully close. Anyway, coming back. Chances are percentage. Percentages come from fractions, decimals, yeah? 5 is how many ways you can get it right, but I need how many total ways that this can happen. 2 exponent 8? No. That is a way for something, but not for this scenario. Does anybody have any other ideas? You guys have taken SAT math, some of you. Huh?
8 factorial.
8 times 2? 8 times 8 times 2.
8 factorial.
You're close, but not quite.
8 factorial times 2 factorial.
Nope. But you guys know factorials are somehow involved. How many pieces of paper are you, or how many draws are you having? 2. So I agree that Kevin with his whole like, hey, there's the first draw, second draw, there's a multiplication. I agree with that. It's called the fundamental counting principle. Ooh, we should talk about that in section 9.6. But here's the idea. How many pieces of paper did you have to choose from the first draw? 8, right? So how many different possible pieces of paper could you draw the first time? 8 of them. If you were to list all 8 of those numbers, right? How could you write out all the different possible pairings, all the different possible draws, I should say? You would write out 1, 2, 3, 4, 5, 6, 7, 8. What did I do a second ago where I was starting to get you guys thinking about how many different possible draws there were? I took the 1 and I said he could go with 1, 2, 3, 4, 5, 6, 7, or 8. 2 could go with 1, 2, 3, 4, 5, 6, 7, or 8. 3 could go with 1, 2, 3, 4, 5. Hey, wait a minute. So you have 8 choices for the first, and you have 8 choices for the second. You're going to end up with an 8 by 8 of all the different possible draws that you could have. But the way you can think about it is, instead of actually listing out the 8, going with all the 8 and saying, hey, there's 64, instead you could just say, hey, there are 64 different possible draws that you could have. And that would be 5 out of 64, which, someone get me a percentage. Not in this one. 7.8%? How do you like them odds? Anyway, so, ready? I said 9.6 and 9.7 had to do with probability. 9.6 is going to help us with things like this and things like this. 9.6 is going to help us with organizing information, with trying to think of how to count up the number of possible ways. 9.7 is going to say, hey, let's start putting everything together to get the percentages. So in section 9.6, actually, does anybody have a book? Can you turn to the odds of section 9.6 for me? Just looking at the answers, not looking even at the questions. The odds in the back of the book. I'm going there too. Some of you are like, oh, I don't have my book. Bummer. But your back probably hurts less. Okay, section 9.6. As you guys are looking at page A149, I want you to look at the numbers. Here, Melanie, look at the numbers. Just look at the numbers. Section 9.6, the odds. Look at the numbers. What kind of numbers are there?
Whole numbers.
Whole numbers. Give me the biggest whole number that you see.
1,800,000.
Whoo! Okay. Can the rest of you guys just trust us that all the answers are whole numbers and they're really, really big? I mean, some are small, like 20 or 40 or 80 or 76. Ooh, there's a 5 billion. Okay, pause. 9.6. Big numbers. How to count up the number of possible ways. Now look at 9.7. What do you see? Fractions? What? Ratios? What? Keep looking. Any percentages? Do you see the difference between 9.6 and 9.7? 9.6 just says, how do we count up how many possible ways something can occur or how many total possible ways? 9.7 says, now let's start taking the ratios and finding percentages. Kind of makes sense, the difference? 9.6, we're counting up. 9.7, we're finding ratios and percentages and chances and odds and all that jazz. So 9.6, here we go. How do we count up? Obviously, we need some help on it because that whole 8 times 8 eluded most of us. Maybe all, but I don't want to just automatically say all because who knows? Maybe a few of my quiet ones work. I thought it was 64. Good job. Okay, here we go. Section 9.6, counting principles. Anybody take an SAT recently?
I took one December.
Any probability on it?
No.
You might have. Well,
No problem.
anybody take the ACT recently? April 14th, the day of the mock AP. Go team. For a calculus. Oh. I don't know. It used to be just mine. Then other people started doing it. Mrs. Leon does. Mrs. Regan, I think she splits it up in her class.
Yeah, we actually do it in class.
Yeah, I think Mrs. Hill does the same way. I think Mrs. Choi does it the same way. Doesn't she split it up? Mrs. Choi used to give a mock exam. I don't know if she still does. Mrs. Leon does. Oh, she gives a full one. I know she gives partials, though. Multitask. What's the old-fashioned way of finding the number of favorable outcomes of a situation, aka the number of ways it'll work, or it'll come out, or it'll be what you want it to be? Find them all. Then count them. Wow. Give me an example of find them all and count them. What's something that... Flipping a coin. Well, I don't know if you want to find them all and count them, but you could, I think. I was thinking flipping a coin, you're like heads or tails. Ooh, heads or tails, heads or tails, heads or tails. So heads, 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 tails, 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 heads, tails, tails. I mean, you could find all the different possible ways of flipping a coin 3 times. Here's another very common one that a lot of you, some of you, depends. You guys don't have good old-fashioned fun anymore. Deck of cards, that's a very, very common one. What are the chances of getting an ace if you pick a card? A lot of you are like, ooh, 4 out of 52. Some of you are like, 1 out of 13, because it's 1 per suit. Some of you are like, I don't know. Sad days. Anyway, go cards. If you want to learn how to count cards, go ask Mr. Che. I mean, he's pretty cool like that.
Why is counting cards bad? Like, I just feel like that's just a strategy.
Because you are capitalizing on. Part of it's a strategy, but part of it is you're just trying to go in and steal money from people. Does that make sense?
I mean, but at the same time, isn't that?
I mean, that's what
Gambling is. Isn't the whole point of it?
You're supposed to go take money. That's a very biblical response. Good job, guys.
Than them, it's not your fault.
Don't worry, we love Jesus. All right, so counting principles. P.S. The we love Jesus was facetious. I know that A, not everybody loves Jesus. B, I know that I don't love Jesus like I should. So C, I was just being funny. All right. But D, praise the Lord for grace. Find them all and count them. That sounds fun. But sometimes there are too many to count, like most of the time. So we need counting principles, formulas, and other clues. That is the point of 9.6. How do we count? In probability. Good job, guys. That counting will only help you if you really want to find all the situations. P.S. Part of the other clues is whether or not repetition is allowed. And some of you guys were having to think through, and you're like, oh, wait, but you put the slip of paper back in. Good. Sometimes it's really obvious to see the clues, and sometimes you got to dig a little deeper. You ready? Set and go. Determine the number of ways. The number of ways. 8 and 4 is different than 4 and 8. The number of ways. A computer can randomly generate one or more such integers from 1 through 12. It's very similar to the pieces of paper because when a computer generates numbers, it generates one number first and then another number second, right? In the programming, it has to choose one first, then choose another second. Let me give you guys a second. Who are we choosing from? Integers 1 through 12. Then you have the characteristics as they're stated. A positive or negative counting number, aka not fractions or decimals. How many integers are divisible by 12? Or no, by 4. Woo, that's rough. What did you guys do? Did you use a counting principle or did you think of all the possible ones and count them? Yeah, Yeah, because you can hold in your head the numbers 1 through 12. You're like, okay, 4 and 8 and 12. That's what some people can do with cards. Anyway, so how many are there? 3. That's easy. Now, what if the computer is choosing two distinct integers whose sum is 9?
3, 6, and 3.
You guys are thinking through the different possible again, right? So far we have 1 and 8 as a pairing. What else?
4 and 5. 7, 3.
We get them all? Those are the possible pairings. Now, how many ways can the computer generate them? Why 8? It can come up with a 1, then an 8, or an 8 and then a 1. If you were to list all the different possible ways the computer could come up with the numbers, those would both be in there. So we'd have to count them both. The 1 and the 8 and the 8 and the 1. The 2 and the 7 and the 7 and the 2. 3 and the 6 and the 6 and the 3. 4 and 5 and the 5 and the 4. Yeah? P.S. The name for listing out all the different possible outcomes is called the sample space of a problem. All the possible outcomes. It's called the sample space. So when I refer to, if you were to list out all the different possible pairings of, I shouldn't even say pairings, but the ways that a computer could, taking 1 through 12, generate 2 of them or choose 2 of them, I'm talking about the sample space. I might start using that more just to make it more familiar to you guys. Okay, the fundamental counting principle. If one event, an event, snazzy name, for the situation that's occurring, like a computer generating a number, like a person picking a card. If one event can occur in M1 different ways, followed by a secondary event, picking a second card, flipping a coin a second time, choosing a second letter or number, followed by a second event occurring in M2 different ways. The little subscripts are just like, we can call them all E's for events and all M's for how many ways. Just the M1, M2 says it's for different events to match them up. Then the number of ways that E1 and E2 can occur will be M1 times M2. If you are a highlighting, starring kind of person, my advice as far as highlighting would be the following. My advice would be highlight the word and highlight the multiplication. Highlight the word and highlight the multiplication. The same exact principle would occur if you also had then an event 3 happening and be times M3, and event 4 happening times M4, etc., etc., etc. The fundamental counting principle. The number of ways event 1 and event 2 can occur. And even when we get to probabilities and stuff as well. And always will be paired with multiplication. And will always be paired with multiplication. But after you guys finish writing the fundamental counting principle and you move on to the example, can you figure out how there's an and? That entire question, there's not one and listed or stated or given. How is there an and in the example? There's no and in the actual question, so why does this follow an and? Okay, fundamental counting principle. If you say the word and a lot, it just starts to sound really, really weird. It's like ant? No, and.
Same with police. Or someone named Toby.
So maybe that's any word. Anyway, so here we come. Where's the and? Anybody find it? Pairs. The and is in the word pairs. Because to choose a pair of letters, don't you have to choose one letter and a second letter? To write down 2 letters, you're choosing one letter and a second letter. If you were to write 2 letters down, wouldn't you be choosing one to write down and then choosing another? It's not that you're doing one or the other. That doesn't work. You're doing one and the other. So therefore, I could call the first blank event 1. How many ways I could choose my first letter? The second blank to be event 2. How many ways to choose the second letter? Okay. Question. How many letters are in the English alphabet? 26. So therefore, how many different options, if you're just to write down a random letter on your page, how many options did you have to choose from? 26. Now, how about the second blank?
25.
Is it 26 or is it 25? 25 would be on the assumption that you can't use the same letter twice. But assuming is kind of dangerous if you've ever heard that phrase. So then coming back, does it say we can't use the same letter twice? Does it say anything about how many pairs of distinct letters or how many pairs of different letters? It says how many different pairs, but it doesn't say how many different letters, pairs of different letters. So therefore, it'd be 26 squared. Yes, you could solve it. Yes, you could figure out how many different ways. Someone have a calculator close and punch it in real fast. 676? Okay. Now, question. Colby brought up a second ago, and we're in honors, he brought up a second ago a factorial. Actually, it was a few minutes ago. He started like randomly writing off factorials, which do come in handy, but can anyone think of what would be the question such that 26 factorial would be the answer? Using letters of the alphabet. What would be the question such that 26 factorial would be the answer? Joseph, go.
Would it be how many different ways can you arrange the alphabet?
Yes. Why does it work? How many different ways could you arrange the alphabet? Each letter can only be used. Think about just like Scrabble. You have one tile for every letter in the alphabet. How many different arrangements? If you had 26 spaces, how many letters do you have to choose from to pick the first? 26. Ooh, but all of a sudden that tile got used. How many choices do you have for the second? 25. For the third? 24, 23, 22, 21, 20, all the way down to you have one little letter left. Multiply them all. 26 factorial is how many arrangements of the 26 letters of the alphabet. What would be the question? What would be the question for 20, or what would be the question that would have the answer? 26 to the power of 26. 26 to the power of 26. Not 26, 25, 24, 23, 22, 21. But 26 to the power of 26. Want me to make it easier? Oh, okay. Go ahead.
Is it if you have a string of 26 letters, then how many ways could you arrange the letters?
That would still be 26 factorial, technically the way you worded it, but what you're thinking is right. I know what you're thinking.
Any letter.
What if you had a computer randomly generate a string of 26 letters? Does that make sense?
Yeah.
How many different strings could it generate? Because then if a computer is generating it and you haven't given it any restrictions, well, it's just pulling from 1 through 26, so it can pull, theoretically, the same letter 26 times, right? So if you have a computer randomly generating a list of 26 letters, it'd be like, well, the computer can choose from 26, it can choose from 26, it can choose from 26. There are no tiles that are being used up. Does that make sense? Okay. But question, how often do you, are you looking for 26 letter words? Not very often. So we have to take those ideas and then make them practical and say, okay, license plates. You only choose so many letters, so many numbers, right? Why are there, as you guys read the paragraph, why am I going to say in a second that we have to consider 6 different events? Why are there 6 events? There are technically 6 events because we have to choose how many different characters. Say it louder. Say it louder. Good. Just as quiet though. Okay, we have to choose 6 different characters, right? But 6 different 1, 2, 3, 4, 5, 6. Think like Words with Friends or something, and you have so many. No, not Words with Friends. What was the old school one where there's like the pictures and there were the blanks and you were trying to fill it in? Oh, it wasn't Pictionary. What was the one you thought, John? Never mind. Oh yeah, you think Hangman. That's okay. Thinking Hangman, except you've been given some hints. Okay, there are 6 different characters that can go on these license plates, the ones that they're talking about in a certain state. Who knows? Probably the state of some unknown, something like, what's the one in Enchanted? No, never mind. All those like cheesy Hallmark movies, there's a random country that no one's ever heard of because it's just randomly somewhere. There you go. Okay, what do we know about the first 2? Okay, we know they're letters, right? Now, even though we know they're, well, we'll just keep going. We know the first 2 are letters. We know the last ones are. Now, hold on, pause. This can be said different ways. This could be said choose 4 numbers, or it could be said choose a 4-digit number. But doesn't it mean the same thing? Choosing 4 individual numbers from 0 to 9, or choosing a 4-digit number, the probabilities are going to be very, very similar, if not the same. To avoid confusion between 0 and O, and between I and 1, the letters 0 and I are not used. Ooh. Okay, if they're not used, then hold on. How many letters do we have to choose from? The letters O and I. Oh, sorry. I read it backwards. I said 0 and O. I apologize. O and 0. And then I and 1. Okay, fine. Those letters are not used. We only have 24 letters left. Pause. Hold on. Numbers. How many numbers do we have to choose from? Don't you have digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9? You have 10 to choose from for each one. You have 10 to choose from there and there and there and there. That's one way of thinking about it. The other way of thinking about it is, hold on, isn't 10 times 10 100? Times 10 is 1,000. Times 10 is 10,000. So there's 10,000 numbers between 0 and 1,000? Ah, but it didn't actually say that we can't use 0 or 1. That's the interesting part. Didn't it just say you're not allowed to use O and I? I know, that's kind of confusing, right? So they said just no O's or I's in the letters. That way all the 0s and 1s will be over there. What would we do to go ahead and solve this guy, guys? 24 squared times 10 to the 4th power. Yeah, 24 squared times 10 to the 4th power. If you guys think about it, a 2-digit number, how many 2-digit numbers are there? 10 times 10 is 100. Wouldn't those be all the numbers 0 to 99? 0 to 99 by 100. This would be 1,000. 0 to 999, that would be 1,000. This would be 0 to 9,999, so there are 10,000 options. Anyway, there are other ways of thinking about it besides 10 times 10 times 10 times 10. But there's the idea. Okay, guys, we're going to keep going on this on Monday for sure. But you guys have the foundation. Ooh, it just might get a little more interesting. However, though, even though it gets a little more interesting, if you just think about each of the events, blank by blank or spot by spot, couldn't you just say, hey, I have no restrictions on this guy, no restrictions on this guy. Oh, but he can't be 0? Huh. Anyway, think through it. There are many different ways to think through the numbers. Get as far as you can. Monday we'll finish up and see if you guys have any questions on homework. Bye. Happy Friday.